Hello everyone. Good evening, Hazel. Hello everyone. Good evening, Zahida. Good evening. Let everyone join in. Then we will begin. Namaste, Paul. Namaste. Good evening, Nitin. Good evening, Aarti. Hello. Hello. Good evening, Hareen. Good evening, Vishal. Let everyone join in. Then we will begin. Today we'll be starting with graphs. Uh, First, we will be introducing graphs, the use cases of graphs, where they are used. Then we will see how to formulate a graph problem, and then we will jump on to some very important algorithms which involve graph data structure. Good evening, Karthik. Good evening, Lalit. Good evening. Good evening, Akshita. We'll begin at 7:10. Let everyone join in. Till now, till then, I can tell you that today we'll be discussing graphs and some important algorithms like BFS, DFS, and we'll then be doing some problems, including which use BFS or DFS. We're doing some really important problems uh, with respect to interviews, so this will be a really important session. Okay, so I think we should start. Everyone has joined in. So, hello everyone. Today is session 4 of this bootcamp, and today we will be learning graphs. We will learn what are graphs, what are the use cases, where they are used, and then we will be looking at how to represent graphs. There are two major ways to represent graphs. Then we'll see when which way is used in which cases, and then we will see some popular algorithms used to graph algorithms which used to manipulate or analyze graphs and are often used in many problems, and many famous MNCs ask these topics including graphs, topological sorting, connected components. So today it will be a really important session. So let's begin. I hope that my screen is visible to all. So today we'll be talking about graphs. Graphs are basically data structures which contain vertices and edges showing relationship between entities. Hello, Arpit. Hello. So this is the major use case. This is the definition of a graph. So you will often see a graph somewhat like this. This is a graph. Hello. Yes, today we will be talking about graphs. We are starting graphs today. Um, yes, and then there are majorly two type of graphs. First, directed graphs. Second, undirected graphs. And the difference is quite simple. Um, difference is in terms of edges, right? So this is the difference. So in a directed graph, if you are standing at U, you can go to V if there is a directed edge from U to V, but you cannot go from V to U. Um, this is U, this is V, this is U, this is V. So you cannot go. You can go from here to here, but you cannot go from here to here. Imagine it like a unidirectional road, right? So it can only go till here. What are the other concepts? Graph is majorly a. It is a new concept on its own. Like uh, you will see at till really high level, graph uh, is considered to be an independent topic. When you actually do really tough problems, then you see some integration of dynamic programming and all in graphs. Till then, you will see graph as an independent topic. So if you're not confident with uh, dynamic programming, if you had some doubts, you have not practiced dynamic programming enough after the first three sessions, still don't feel like you will not be able to understand graphs. Graph is completely independent of dynamic programming. Although dynamic programming is integrated in some problem of graphs to make it a little tough. Yes, like you will see some problems using segment trees on graphs, uh, segment trees plus graphs. But like when it comes to interview preparation, you don't really need that much of in-depth knowledge of this topic. So we will be covering decent amount of uh, algorithms. We will not dive deeper into using Fenwick trees or BIT in graphs. We will not do that. But honestly, that's not even needed when it comes to um, interview preparation. So where were we? We were talking about difference between directed and undirected graphs. So this is a directed edge. This is an undirected edge. Obviously, the difference between direct and undirected graph is that this one contains directed edges and this one contains undirected edges. Okay, so we will be talking about theoretical part mostly in the first 15 to 20 minutes. So bear with me. Then we will jump on to the more interesting portion, which will be solving problems. Uh, Two ways to represent graphs. First is adjacency matrix. So this method of representing is quite simple. So let's imagine that you have v vertices. So you basically create a v cross v matrix. This is a matrix M which is v cross v, and so and you will fill this matrix as follows: Mij will be equal to 1 if I comma j belong to E. Mij is equal to 0 if I comma j does not belong to E, and E is set of edges. So Mij entry will be 1 if I comma j vertex I comma j edge is present in the set of edges, and if it is not present, then it will be 0. So this is how you will be representing the matrix using representing graphs using adjacency matrix. So just for to give you an example, like 1 2 3, yes. So adjacency matrix for this will be 1 2 3 1 2 3. This will be the adjacency matrix, right? I mean, for there is another fact you can see that for undirected graphs, this matrix, um, it is just for undirected graphs, M equal to M transpose. You can see this, right? So because two edge from 2 to 1 and a h from 1 to 2 mean same in undirected graphs. So transpose, for those of you who don't know what's the transpose of a matrix, you simply like, for example, this is the first row, this is the second row, this is the third row. You make the first row the first column, the second row the first column, and the third row the first column. You basically uh, rotate this. You don't really rotate. You make every row, you swap with every column. Basically, you swap r comma I, swap with ci. That's how you create a transpose of a matrix. So clearly it is going to be, basically transpose means that this matrix is going to be symmetric on this line. The part on this, the part which lies here should be equal to the part which lies here. The reason behind this is that these things are equivalent. Like one connected with two and two connected with one makes the same, uh, means the same in undirected graph. So this is how you represent graph using adjacency matrix. Now the second way is, now think about it. What's the need of representing a graph in a different manner? Like, why were we not happy with adjacency matrix? Why was there a need to introduce another way to represent graphs? Think about it. Like, just look at this. Let's say I add one more fourth edge, which is not connected with any of the edges. Think about how this matrix changes for the fourth vertex. Think about it. Uh, can you think of it? What is the problem with adjacency matrix approach? Like, if we are representing this graph using adjacency matrix, what is the issue here? Like how the matrix will change. I mean, what the matrix will look like. Where can you think we can optimize it better? So in data structure and algorithm, you only think in two terms. You can maybe save time or you can maybe save some space. Which one of which one of it do you think we will be doing here? I'm just asking you the logic behind introducing a second idea. Okay, so first let me just discuss the second representation. Maybe you will be able to figure out what are we optimizing. Uh, Adjacency list. Okay, so in this one, you basically create a of list of size v cross. You create a list of size v first. Basically, the total size of the list is somewhat like this. Now this might be a little tricky, or is it like this? No, it's not. Sorry. The idea behind this is the size is basically like this. Size reduces to this. Now think about it. Is this compare these two quantities? Yes, Aryaman, I will share them. I will. I will tell you the resources in the end of the session. First, let's focus on what's going on, right? So I'm trying to like give you an intuition why we are trying to make adjacency list. So what do you think will be bigger? Is this value bigger or this one? 2 times mod e is bigger or mod v into mod v? So mod v is number of vertices and mod e is number of edges. What do you think? Which will be bigger? Mod. So clearly, like it's pretty clear that this is going to be the case, right? So what we do in adjacency list is, for example, there is a node u. You only add those vertices plus one and so on, such that vi comma u belongs to e for all u. So what you do is, let's take an example for that same graph. For this graph, this will be our adjacency list. You can clearly see that we have optimized this using 4 blocks here instead of 9. So we are basically, there can be a case where our matrix is sparse. Sparse, what do you mean by sparse? There are more zeros than ones. So you can think of this like 0 is basically wasting my space. I don't want zeros, right? There is no information I get if I know that there is no edge between this. There is no gain. I only get some useful info if I know that there is an edge between u and v. So I only need to store that information. Uh, so that's why we only retain these ones in our adjacency list. You can see clearly only these vertices are retained, right? Exactly, Shraddha, exactly. So what we have achieved, what we have achieved through this is space optimization. But if someone asks, "Ki- If someone asks you that what's the best way to store graph, to represent graph, adjacency matrix or adjacency list, what will be your answer? What will be your answer if the interviewer asks you that, then what's the best way to represent graphs? What will you say? Adjacency matrix or adjacency list? You can answer on the chat. Okay, Saurabh says matrix. Matrix. Okay. We already saw that list helps us in optimizing space. No one is saying list. Okay, Nitin and Ashwin says list. So list. Okay. Actually, you all are right. Like, there is no definite way to represent graphs. It depends on the use case. Now you will be saying why. You can clearly see you have optimized space, right? There must be something we have sacrificed when we did this optimization. So the sacrifice we made was, see, till now I hope every one of you this much of programming, that how you will be representing these graphs. You will be representing by 2D arrays, right? In a 2D array, you can simply access a location in constant time. So if I ask you, so like Nitin said list, right? So Nitin, if I ask you that in your representation, if I ask you, is there an edge between 1 and 2, what will your algorithm be? You will say simply do a linear search in the array of 1 or in an array of 2. So if you find 2 in the array of 1 or 1 in the array of 2, then you say yes. Otherwise, you say no. And what's the complexity of this? O of n. Whereas in matrix, the complexity of this is O of 1, right? And many of you also said matrix, like Saurabh and Shraddha and Priyadarshini. See, if I ask you in your uh, representation, I have I have 1 and 2 connected like this, and then I have 3, 4, 5, 6, 7, 8, 9, 10. I have uh, a million users, and just 1 and 2 of them are friends. Then I will ask you, why are you using 10 raised power 6 cross 10 raised power 6 space? You are just wasting the resource of the company. You can clearly just use this list, and the list will be having 1, 2, 2, 1, other will be empty, right? So it depends on the use case. Um, yes, Shraddha, you are right. Like mostly you'll be using adjacency list, but don't get confused that this is never used. Like there are cases where this is used. So there are use cases where there is only a need of accessing and searching for the data. And if you're just accessing and searching, obviously adjacency matrix is the one. But um, if your job is to manipulate the data, you are really concerned about the space complexity, then you go with adjacency list. So don't give a straightforward answer. There is like it depends on the use case. So let's hop on to the question of how do we formulate a graph problem. Um, Let me just give you a scenario, and you have to tell me how will you create a graph out of this. So you have some n friends at a party. You are given the friendship chart. So friendship charts kind of looks like this. That Akhil is friends with, let's say, Soham. Um, and Saurabh, let's say, is friends with uh, let's say Nitin is friend with Ashwin. Ashwin is friend with Soham. This is the friendship chart you all are given. Okay. Now tell me how you can create a how you can create a graph out of this. You have to create a graph representation of this scenario. Give me a graph representation of this scenario. Like by graph representation, I mean what will be your vertices, what will be your edges. How will you create a graph out of this? So the question is, no, I mean like graph representation like this. This is a graph pictorial representation. I am asking for uh, no, just tell me what will be the vertices and what will be the edges. Like, just tell me what will be the vertices. Like, what was the definition? Graph is basically used to represent entities via a relation, right? So tell me what will be the entities and what will be this relation in this problem. Think about it. So here simply vertices can be names and uh, edge can be friendship, right? So if I have to convert it into a graph, I can simply do Akhil is friends with Soham, and then Soham is friends with Ashwin, Which one is friends with Bitcoin? Or is friends with Satan? So this will be the graph representation, right? This means these two entities are friends. Simply we created a graph representation of this. So now if I ask you, um, how many friends does Soham have? So you can just say the in degree of Soham. In degree means number of incoming edges. So there are two friends. Answer will be two. Oh, sorry. Yes, for Soham the answer will be two. Right. That's how you can formulate a graph problem. Yes, you are right. They are not connected. This is one connected. This is one connected component. So now coming on to the concept of connected components. What are the connected components? So you can simply we can actually take this example. Oops. Okay, so see here we have two connected components. You can see it. So what is connected component? Every entity U belonging to S, connected component S is reachable from now what is the definition of reachable? What do we mean by reachable? Reachable means there exists a path from U to V. Okay, so see, this is reachable from every vertex, every entity of this component. This is also reachable from every vertex, every entity of this component. Hence, this is a connected component and this is a connected component. Okay, so we have actually talked a lot about the theory part. Let's just jump onto some graph algorithms. We'll be talking about many graph algorithms. Let's just talk about BSS. BSS. Search. Okay. I mean, is there any doubt to anyone before going to graph algorithms? Is there doubt? Is there any doubt to anyone about whatever we have talked till now? You can ask in the chat. Now we will talk about BFS and DFS, and then we'll be jumping on to some problems of BFS and DFS. Till then, you can tell me if there is any doubt. The relation have attribute. If there is any doubt, you can ask it in the chat. Then we'll be jumping on graph algorithms. Okay, okay. So I have posted the attendance link is in the chat. You guys can mark the attendance. Yes, Phoenix, we actually do backtracking in DFS. Okay, so I believe everyone has marked their attendance. So what do you do in a breadth first search? So let's say you have a source. What you do is First, you process every adjacent node of the source, and then you process the next adjacent nodes. So it's simply sort of like a level order traversal. This is the second, this is third, this is fourth. So how you will process in this case is 1, 2, 3, 4, 5, 6, and then 7. Let's see the pseudocode of it. You will be using a data structure known as queue. While queue is not empty, u is equal to front of queue pop queue v belonging to adjacency of u if v is not visited mark v visited push v into queue. That's what you do. I hope the pseudocode is clear to all. If there is any doubt, you guys can ask. Now, note two things. This is a pseudocode, so Q is a Q. Uh, then V is not visited, so you might be using some set or a vector visited to ensure this condition, right? Now let's jump on to a problem. Let's just solve one problem. What will that problem be? Let's solve number of provinces. Try to think about this problem. And also one thing, um, notice that uh, notice that you will only visit the node if it is not visited, which means uh, you will only you will only run this loop for v times. So the time complexity of this is O of v, which means number of nodes. Keep a note of that. Try to think about this problem. Try to think of an idea how you can solve this problem. So the problem is asking for number of provinces which are directly or indirectly connected. So they are essentially asking for number of connected components in the graph. Can anyone figure it out? How you can proceed in this problem? So first they have given you the graph in matrix form, right? I guess those people who are saying the matrix is useful, they'll be quite happy. Saurabh, Priyadarshini, Shraddha, you guys will be really happy. They have they have chosen graph matrix representation of graph. Yes, Tatvik, yes, Akshita, you're right. Q uses first in, first out principle. Kind of imagine Q as a tunnel and stack as a cave. So a cave is this is the entrance of a cave and it is locked from one end. So if people are coming inside a cave and then the last people comes in, so the person who came in first will obviously be leaving the last. So because he want in order for him to leave, then you want these people to empty the cave. So think of it as a cave and think of Q as a simple tunnel, right? A simple tunnel, like this is the opening of the tunnel, this is the uh, ending of the tunnel. In order to go from here to here, the first person who enters the tunnel will be the first person going out. That's how you can imagine the working of a queue, because that's exactly how queue works. You kind of insert it from the behind, and then the first insertion is indeed the first output. First in, first out. Will we be having same questions in actual field? Uh, can you be more clear, Saurabh? I didn't understand your question. I guess everyone has uh, read this problem. You know, it's quite simple. You're given a graph. Yes, Debajyoti, you are correct. You can use by DFS or by BFS. For now, we'll be doing by BFS because we know that only. Simply run a loop, go to every vertex. If you go to a vertex which is not visited, call BFS. You know that BFS will indeed uh, traverse every vertex of that component. So it's essentially how many times you call BFS on non-visited node. Same kind of, uh, not same kind of work. I mean, it's uh, similar to this. Like if you will be building some low-level application like Redis database and all, they actually use this. In fact, um, the most efficient databases are based on B trees. You will study them, or maybe you might have studied them. Um, that is actually a example of graphs, B trees, and they are heavily used um, in in optimizing databases. Like you must have seen Postgre database, PostgreSQL, MySQL. You guys must have used. They actually, the inner working of them, they actually use B trees, and B trees is a type of graph. I mean, tree is a subset of graph, right? You must know that just a connected component that does not have a cycle is known as a tree. So yes, actually you can use DFS or BFS Bhavika. For now, to introduce you, I'll be using BFS in this problem. Um, then we can. Yes, yes, you are right. Visit all the cities. Yeah. So this problem can be solved in simply apply BFS. Mm, we actually need just 10 vertex for this. And you, okay, yes. Oops. We wanted V here. Oh, we are not got the V. Yes, this should work, and it works. So, is there any doubt to anyone in this problem? I can discuss it. You simply like call BFS the number of times, the number of connected components there are. I mean, I am using BFS. You can use DFS as well. You just need to traverse uh, the cities, right? I guess someone pointed out that DFS will be used. Uh, Bhavika pointed out that DFS. Yes, you can use DFS in this. I use BFS because uh, I wanted to show you the implementation and all. So this was the exact pseudocode uh, we talked about. Okay, so I believe we should solve another problem using BFS only. This is another problem. Very try to focus on the concept, right? The last problem was pretty simple. I understand. It was just using BFS. Now this will be a little tricky. I get stuck during implementation or writing the pseudocode. Okay. I mean, if you're solving problems on lead code, then you should try to write the algorithm 4 or 5 times, right? If you are learning DFS, just like in today's session, you will learn how to write BFS, right? Like, um, look at this code. This is actually the code of BFS. This. So try to understand it. Try to write 4 or 5 times. I mean, even if you like, that's what I do. Even if you don't understand it, try to write it 4 or 5 times. Like first, try to build a muscle memory for an algorithm. In like while applying it 4 or 5 times in different problems, you will be able to understand it. But if you will write it 4 or 5 times, then it will help. I guess it will help in terms of implementation. Uh, I'm talking about lead code problems because they are generally very straightforward. If you know the algorithm, then write that algorithm and it will be accepted. If you're talking about um, if you're talking about code forces and all, then you can solve this. You can solve you can solve this ladder A2 ladder. This contains some really nice problems. Like they do contain some really nice problems. You can do less than 1300 rated problems. Okay, if you are doing lead code, then do then try writing that algorithm you are learning. Try writing it 2 3 times, and then try to do some 5 6 problems. Uh, you will be good to go. Yes. So read this problem. We'll be using a new concept here, which will be multi-source BFS. For now, we have used BFS from a source. In this problem, we'll be introducing a new type of algorithm, which is multi-source BFS. Yes, exactly, Debajyoti, you are right. So this is the question of um, number of provinces. Now we'll be doing and tomatoes. So it's pretty simple. We'll be introducing multi-source BFS. So see, for in the first single source BFS, you only had one source, right? Like look at this. Uh, Rather than looking at this was a code for BFS, right? But in order to enter in this loop, you must insert something in this queue. And you might have noticed that in this problem, we just inserted a single value. The only difference, the only difference between this single source to multi sources, you run simultaneous BFS for multiple locations. It is actually simple as that. So you will be having, for example, two nodes, and then you run BFS simultaneously. Like I'm just trying to visualize how the BFS, oh, no, how the BFS is running. Okay, I hope that everyone is able to realize it. Let's say, let's say this is the graph, and you run BFS simultaneously on this and this. This will the BFS, right? This will be the first level. This is the zeroth level. This will be the first level, and now this will be the second level. Simultaneously, this will be the second level because you're doing it simultaneously, right? I will just show you the levels of this. I hope this is clear how a multi-source BFS works. Now, simply what this problem asks for is you have a grid. You have oranges like this. And now some oranges are rotten. Okay. Now every orange will get infected in a second, which is connected to an orange. And what's the definition of connected? That it should I share one side. Like for this is how the definition of connection means. You can simply run a multi-source BFS on this one, right? So let me take the only modification you need is you take a queue of int comma int, and then you keep in your queue what's this 1 comma 2 and 1 comma 4, sorry, 4 comma 1. What is this 1 comma 2, 4 comma 2? So you simply 1 comma 2, 4 comma 2. This will infect, this will be the state at 0 second, first second. The state will be 1 comma 2, 4 comma 2, 5 comma 2, and 1 comma 3. Why? Because this orange will infect this orange, and this orange will in fact infect this orange. So this will be infected, this will be infected, and then the second, which oranges will be infected? This orange will be infected, this orange will be infected, and also this orange will be infected because they are the neighbors. This is 2 comma 3, 5 comma 1, and 5 comma 3. No other orange will be infected, so the BFS stops here. Is it clear to all that the BFS will stop here? So no, all oranges will not be infected if the if the grid would have been like this, then the answer would simply be 2. In 2 seconds, the grid will be infected. So let's see how we can code this problem. Hmm, we can actually take this code and simply take this code from here. Yep. And now we need uh, let's write the code. I'm just defining some macros to save time, so I can use pi here. How can I? Okay, just insert uh, a dummy of -1, -1. It basically tells us that these oranges were infected at this second. So we can increase the time. Q.empty pic is equal to q.find q.up. And then we can also directions -1, -1, -1. Okay. Here we will be declaring the visited array. We also need to keep a count of visited ones, right? So this is done, and visited of c.account, c.stream. Done. Actually, instead of visited, we could do equal to 1. We don't need a visited array here. We already given an array G, right, representing oranges. We don't really need. We just need to go to a fresh orange, right? There is no point of going to a rotten orange because it has already been rotten, and there is no point of going to an empty space because there is no orange there. So we can just go to a fresh orange. We can use the adjacency matrix itself because there is no boundation. We can change the adjacency matrix, right? So um, I mean, not the adjacency matrix, the grid given to us. We can change it. So q dot push p dot fi p dot c. Oh, there's no variable named answer. Let's wait for some time. Okay, so this gives 0. What's the problem? Okay, so the problem is we are never increasing this timer. So what's the logic of increasing the timer? Whenever we hit a minus one comma minus one flag equal to minus one and q dot s equal to minus one. Okay. Oh, there is no need variable name the answer. Fine. And we also need to check if all the oranges are rotten. If we find any orange which is fresh, this means there is no way to rot the entire grid. So answer is minus one for that case. Oops. Okay, what's the point? Okay. So we just need to handle this edge case. And that edge case can easily be handled like this. If all the oranges are rotten at the first glance itself, not even this, maybe we can just modify our BFS function. Okay, then just do the push. Yep, this should accept now. Yes, it is accepted now. We have used multi-source BFS. This is used for directions. This is this nested loop is used to identify the sources where initial rotten tomatoes are placed, and this is the implementation of multi-source BFS. And this is to check if every tomato, every orange has become, every orange has rot or not. I hope it's clear to all. It's been a long session today. Uh, I hope BFS and multi-source BFS is indeed clear to everyone. Try to think about this problem before coming to the next session. A really nice problem, a hard problem, but it will be really easy if you think it in terms of graphs. So try to solve this problem before coming to the next class, and next class will be really important as we will be discussing about DFS, topological sorting, Kahn's algorithm, and some more algorithm. If we will be having some time, we will try to discuss Dijkstra as well. So if there is any doubt to anyone, you can stay. Otherwise, the session is over for today. Yes, that technique also works, Shraddha, to use GPT if you have the idea. But try to you know create a habit of writing, coding down your idea as well, because that creates a strong grip on that coding language. And if you will be asked to code it in front of the interviewer, you will not be nervous at that time. So if there is no doubt to anyone, I think we will end this session here only. Try to practice BFS and multi-source BFS. Someone was asking about, thank you, Debajyoti. I think someone was asking about resources they can practice on. You can go on this sheet, Striver sheet. You can practice this really nice sheet. Then you can practice this SD sheet. You can also practice. You can also practice from this topic list. But don't. I would suggest that if you have a good grip on lead code, then only go to this topic list. It's a really comprehensive list. Uh, Otherwise, just try to solve problems from these. When to use BFS? Um, Basically, when you need to find BFS, you will uh, you will understand it while solving many problems. So there will be problems where you will be asked to calculate some time uh, based on some conditions. Uh, for example, like uh, in problems like shortest path, you will be needing BFS. Uh, Basically, in any problem, if you need level order traversal, you try to think of BFS, path finding problems or shortest path problems. Okay, so I hope it's clear to everyone. We will end the session here only. Have a great day. Okay, we will meet tomorrow at the same time for the last session of this boot camp. Bye bye, everyone.